Okay, hello everyone. So this is the quick video to run and do ENG 783 for the design with composites theory and practice. So this is looking at the assignment. So just quickly go overview with the assignment quickly again. So what we're expected to do here is obviously, first of all, we're going to be conducting a classical laminate theory study on a unidirectional epoxy composite 8-ply subject to a cantilever bending test of 10 newtons using the following material properties provided, and several assumptions have been made. So these are the assumptions that are taken, and here is an image of just showing you the cantilever bending test for the validation. So the material that we're taking is from the ANSYS database for a unidirectional composite epoxy material. So density, Young's modulus, Poisson's ratio, shear modulus, tensile strength, compressive strength, and shear strength is all provided. We've got the dimensions here. So the length is 80 millimeters, width is 13, total thickness will be 2 mil because the ply thickness is 0.25 and the number of plies is 8 and the force is 10 newtons. Once we've calculated, done the classical laminate theory, you must obtain the stress of each ply respectively and obtain the beam tip deflection for numerical comparison. So using ANSYS, you must now conduct a validation case and compare your results against the classical laminate theory, comparing the stresses, respective plies, and the beam deflection. Once we've done that, then we can conduct a parametric study on the beam using a 3-point bend test. This is an example of a bend test that we're doing, and numerically investigate the flexural properties. You are required to use a stacking sequence that is quasi-isotopic and symmetric, and comparing the maximum deflection and stresses respectively for each of your parametric studies. And as you can see here, the dimension of the support span is 64 millimeters, support radius and loading nose is 3 millimeters each, and the load is 250. Now, if you wish, you can do additional loads for comparison, and also you can change the material properties as well to do a comparison study. And again, the word parametric study here is defined by yourself of how much in depth you want to go into in regards to getting further additional marks. Finally, discuss and summarize and conclude on your findings of the numerical model. And as I said, this needs to be presented as an IEEE conference proceeding paper. So, with the assignment shown now what to do, obviously here you must first make sure you have your Excel sheet that you should have done and obtained for your classical laminate theory. So this provides all the calculation for your classical laminate theory. So let me just put that over here. So you can see here you got all the data for your material property that you've inputted, and then once the calculation goes through, you've got your layer thickness, you've got your load value here that you can see, 10 newtons times 80, which is the length divided by the width. That's here. And then obviously down, as you calculate everything through, you start getting your values. I'm just going to quickly just do it this way. So you can see here, you can start getting your stress values of your ply 1, your ply 2, your ply 3, and your ply 4. And as you can see here, these are the top values here, and you can compare them with your ANSYS values. And again, using your theory here, you can start looking at your deflection. So the deflection here is minus 1.63 millimeters. We've got our length and our force, P, of 10 newtons. So once you've got your classical laminate theory calculated using Excel, we can start working on the validation case. So again here, open up Workbench, and the first thing we want to do is drop in an engineering data. So we set our data first, double click on engineering data source, go to our composite materials, and what we want to do here is we want to use the epoxy carbon unidirectional prepeg here, and as you can see, it provides exactly the same material properties as we've seen before. So here you can see you've got your modulus, harshness ratio, shear modulus, and then all the other tensile, compressive, and shear stress values as well. So all we want to do is we want to add that to our library. So you can see it's in our library now, and we've got our engineering data source. So we can see here we've got structural steel and we've got epoxy carbon unidirectional 930 GPa pre-peg. So now that we have that, we can close our engineering data, and now we can drag and drop an ACP pre. So if you click onto this, hold the left mouse button down, you can see there's a variety of green boxes that have appeared. And what we want to do is we want to drag and drop it on to the engineering data, and you can see that's highlighted red now. Let go of your left mouse button and you'll see that has transferred this data into this engineering data here. So now what we want to do is we want to create our model. So right click on geometry, edit, new design modeler. We don't want to be using space plane or discovery or any others. Just to let you know that this version of ANSYS is the 2023 R1, as some students are using the latest software. So I recommend either downloading the new one if you're doing this remotely, but on the university campus we have 2022 R2. So give that a few seconds for it to load up, and you'll see that the loading up is on the bottom left hand corner where it says starting up process. So once this is opened up, what we want to do is click on the look at on the XY plane. That just gets us into our view, and here's our orientation. Change the units to millimeters, so it's fine, and you can just press look at, and that'll bring that into scale. Now we're going to be making our panel in the ZX plane, and it's going to be layered up in the Y direction. So here we've got the ZX plane. If we look at this now, and you can see that this is the global X direction, so we want to draw our panel in this way. So our first section that we're going to do is just a rectangular box, something like this, and we're going to give it some constraints. So symmetry, middle axis, left edge, right click, new axis, x-axis, top edge, bottom edge. And that's now fully constrained. So now we can go into the dimensions and give it a general dimension here. And we know that this is 13 millimeters and this is 60, is it 60 or 80? Sorry, 80 millimeters. Just to double check. So we can see here 80 by 13, that's correct. So we have this now. Now what we can do is we can generate this into a surface. So surface from sketches, selecting our sketch 1, apply, and we know that this is 0.25 millimeters thick as each ply as it is. So that's we have here. So we got our surface body, and we can just name this one PLY. Say that this is 1 ply. We can now go File, Close Design Modeler. Now what we want to do is double click on the model and apply a mesh on this. So just give it a few seconds for the mesh to open up. And again, on the bottom left hand side you'll see it'll give you your value, it'll tell you if the mesh is running and opening up or not. So what we want to do, give it a few seconds to load up the actual model. And what we want to do is we want to use the edge selection tool and use a global sizing to make sure that the mesh is all in a quad direction. But before we will do that, we want to just go to our ply, and here where it says offset type, what we want to do is we want to change that to the bottom. So it just means that the offset, when we grow our mesh and our plies, it starts from the bottom, goes upwards. So that's that done, which is absolutely fine, and the material obviously is epoxy carbon. Now what we want to do is insert in a mesh, insert sizing, select all the sizes. So Remember, control gives you multi-select function, so pressing control allows us to select all those edges, press apply, and we can give it a default 1mm would be fine, I think. So giving it a 2 should be absolutely fine for this, but obviously just be careful with student licenses. But if you're working at university, you can give it just a 1, should be okay for now. So 4 edges, 1 element size, and then what we want to do is mesh, insert, sizing, face meshing, apply face meshing, and that will be all nice and quad. And our global size there, we can change that to 3.5, and then right click, generate mesh, and we should have something like this. Now you could, obviously improve that mesh depending on your student version of the license, or you're using the university license, but I believe the new 2023 doesn't have any sort of restrictions on the node element side of things. So, but then again, it depends on the PC power that you have in order to run this kind of simulation. So keep it like this is nice. In general, you can take this forward if you wish later on. But what you can see is that the mesh has grown in the Y direction. Comparing to your dimension here, you can see that mesh is going up in the Y direction. So File, Close, Mechanical, right-click, Update, and you always want to have green ticks as you go along with ANSYS. So a green tick means that it's ready, everything's fine, and you can go ahead to the next step. So now what we want to do is go on to the next step. And ANSYS ACP will open up. And as you can see here, we've got the material database. So what we want to do is just press the lightning strike, and we have our material that's come in. We want to right click and create a fabric, and you can call it fabric 1, leave the names, it's absolutely fine, it's up to you what you want to call it. So here I'm going to leave it as, I can call it, to say that it's a composite material, and obviously carbon fiber epoxy. Make sure your units are in millimeters, otherwise you're going to get some crazy values. So again, materials, just bring that back in again. Oh, fine. And then here, material is epoxy, comp, unidirectional. The thickness is 0.25. Press apply. Now, if you don't have a small value here, it means your units are still in meters. So, to have a very small value means that it is in millimeters. So again here, just be very careful to make sure your units are correct. Once you've done that, press OK. Now what we're going to do is we want to create a stack up. So the stack up here, it's basically from the bottom up, going upwards. And you can just call it stack up 1, it's absolutely fine. So comp unidirectional, they're all unidirectional, so there's no angles. So 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 plies. Press apply, and you will see the thickness is 2 millimeters, so you know that this is correct, and that's fine. Okay, so bottom up, press OK. We've got the elements, so update all elements, which is good, and that's nothing really, it's just saying all elements are done. Now what we want to do is we want to create a Rosetta, so create Rosetta, and we've got the direction here, x equals 1, y equals 1 for the direction, which is fine, so apply, OK. Now what we want to do is oriental selection, so create an oriental selection, and see the element set here. If you click between the 2 brackets, okay, put the cursor there, you can go to all elements and click all elements, and it will fill it in automatically for you. Same with the Rosetta. And here, all we want to do is saying the direction is going in the plus y direction. apply, okay. Modeling group now, so create a modeling group, okay, and then create apply. Now here again, the oriented selection is this one here. Apply material is not the material itself, but it's the actual stack up that we've created. So once you've done that, press apply, press OK, and then what we do is go to the solid model, create solid model, element set, all elements, and again here, nothing else, leave everything quite standard, apply, OK, and you'll see here it's created our model that we can see that is unidirectional and is 2 millimeters and it's going from the bottom going upwards. Okay, so with that done and in place, what we can do now is go File, Exit, update our ACP. And what we're going to do now is bring in a static structural, and again remember, left click, hold on, look for the green boxes, and now what we're going to do is we're going to drop it onto the model, and you can see here it will automatically take that through. So here now, oh sorry, delete. We don't want to drop it onto the model, we want to drop it onto the setup. So it's static structural. Ooh. Just 1 second. Static structural, drop it there. Select the model. Okay, so it's a little bit tricky that what we did there was you can't just drag and drop onto that one. You have to have a static structural and you have to bring it in as a solid composite, not a shell, but a solid. So once you transfer that, it will automatically delete everything else that was in the static structural, and now it's going to use the model from there in order to run the simulation. So what we're going to do is double click on the model. Okay, so here we have our model in itself, and we can see here we just need to solve that quickly. We've got a solid model, okay, composite material, that's fine. So we've got the mesh, which is good. We've got static structural here, and just make sure that there's nothing. Okay, that's fine. So here what we want to do is we're going to do some environments. So we've got a fixed support on this, and here we've also got insert a load, so a force on this edge here, apply. Will it allow us to direct? Nope. So surface, and it's minus 10 newtons. So let's just quickly press solve now. Okay, so that's fine. So here what we can do is we just have a look at some total deformation. So press solve. Okay, so you can see the deformation here is 1.6338. So if you go back here, you can see here it's in the minus direction, 1.63833. I mean, goes to 3 decimal points, but you can see that that's exactly matching with our calculation here. And here now we need to compare our top layer. So apply 1, apply 2, apply 3, apply 4. So here, if I add in a stress of normal, but here we want to select apply, we go to the imported piles, and here you can select the bottom one, which is the top ply, and so apply, we want to do top on there, press solve, and you can see that's 97.38. So what we're going to do is we're just going to quickly just duplicate this, duplicate without results, duplicate without results, duplicate without results, because it's symmetric, so we just use the 4 plies and we compare those. So here again, this is going to be the second one, this is going to be the third one, and this is going to be the fourth one. 1, 2, 3, 4. Apply. So press solve. So again here, going to the first one, 97.38. So it's a bit way off, but we understand that it's very close to the contact region, so it's going to be slightly quite high, but it's still okay. Stress 2, 69.96. So you can see here it's getting a bit more closer, 69.96. And then stress 3, 46.08. 46.08. And the last but not least, stress number 4, 22.89. 22.89. Okay, so you can see very, very close results. And again here, you know, that's your validation compared, and it's completely fine. So that's how you would do your validation case for the simulation, classical laminate theory against your theoretical, against your numerical values. Obviously you need to make this a lot more nicer and tidier. You need to be able to put this into a table format for your paper. And in the paper, everything you've done for the classical laminate theory needs to be, you know, rewritten and put into a very good format with all the equations and calculation. You don't need to show the calculation, but you can show your results of your calculation at each level and each stage. So now that we've done the kind of validation case, we can close this down, and what we can do is we can use this workbench again for the 3-point bend test. So again, you know, using the same ACP panel, which is absolutely fine, but what we do want to do is we want to basically make our 3-point bend test analysis. So we want to drag in a mechanical model and drop it here, and in that mechanical model we're going to create our noses for our support and bend. So again, new design modeler, and again here, XY look at, make sure the units are in millimeters, XY look at, and straight away we can just draw a quick sketch of a circle there, circle here. If you get the R to match, that's really good, and another R to match there, which is really good. And again here, constraints, symmetry to the center of that one, to the center of this one, so that's nice and symmetrical. And what we can do is we can give it a dimension. So we know that the radius of these are 3 millimeters, so the diameter is going to be 6 mil. We also know that our composite panel was made in the Y direction, so it's 2 millimeters up high. This is 3 millimeter radius, so this from the center from there to the axis here is going to be 5 millimeters. So using a horizontal tool measurement from there to there, we can say that this is going to be 5 millimeters. We also know from here to here is 3 millimeters. And as you can see, they moved. If this one hasn't moved with this one, just put another dimension in there to make that one grow. Now we know that the support span from the thing here, you can see says that the support, where is it gone? Support span is 64, so 32 millimeter each side. So again here, using a horizontal, we can go from there to there and say that this is 32 millimeters. Okay, so we can see that there. Now what we can do is we can extrude these each way, because obviously they're 13 mil. They have to be the same dimension as the composite panel that we've created. So being 13 mil, so 6.5 millimeters each side, will give us our thickness for these support and loading. So all we do is just extrude, sketch 1, apply, add as material. Now here we just put both symmetric 6.5, generate, and you can see that it creates our model here, which is absolutely fine. So now that we have this, we've got our parts, we can file close design modeler. Now what we want to do is we want to drag and drop another static structural, because this is going to be the 3-point bend test. So static structural, drag and drop it there. And again, the setup here will come into the model. Let's transfer it as a solid composite data. And the model here will go into this one as well. We just need to refresh this one. Give it some time. Update. Okay, now double click on the model. Give it some time and the static structural should load up. Okay, so we should have the mesh here, so you can see it's generic mesh, not really important with these, so don't worry about that. But you can see that the 3-point bend test specimen is nice and ready. Now obviously what we want to do is we want to put in some supports and stuff. So here we can go to faces, select these by using control to do multi-select. So and then put in a fixed support. So you've got 6 faces on a fixed support. We've got this one where it's going to be our load. So here again, there's going to be a force on those 3 faces in minus 250 newtons. But at the same time, we want to put in some displacements. So again here, we want to put in a displacement for this nose beam in here. We want to say that it's free only in the Y direction, but not in the X or Z direction, meaning it can't just roll off. It can only move in the Y direction, up and down. Also at the same time, we can put in a remote displacement on this composite panel as well. So we've got all of those. Right click, insert remote displacement, and what we want to do here is the displacement in the X, it's free, in the Y it's free, in the Z it's not free, because we don't want it to fall off or come off the beam in that direction. But also at the same time, we've got some kind of connections as well. So in the contact regions here, we've got this contact here. Rather than being bonded, it just means that there's no separation going up or down. And these two are frictionless. There we go. All right. And then if we just right click and press solve on the solution, it may come up with a little error message, but don't worry about them. It's absolutely fine. Give it a few seconds. Ooh. You can click on this so you can observe and see what's happening. Okay, so that took a bit of a time, but it should be fine. So now you can click on your deformation, so total deformation, total stress, so normal stress. And here, rather than doing plies this time, we're just going to do the entire selection. So press solve. So you can see the deflection here is around about 0.05 mil, which is, around about right for this kind of unidirectional material, because remember it's all in one direction. So it's always going to be nice and strong in this way, and we've got the normal stress value here as well. Now, obviously what we want to do is we want to be able to compare these. So again, here taking a value, which is the maximum value, putting that into a table, and then the normal stress for the entire selection, putting that value into a table, which is really, really good. So what we also want to do is be able to take some other kind of measurements as well. So if you go into the geometry and into the model, insert a construction geometry and create a path. Now, obviously, this is 2 millimeters thick, so 1 millimeter there, 1 millimeter there, and it's 80 millimeters, so minus 40 plus 40 will create a line generally in the center of our model. So what we can do now is we can insert in a solution, deformation, total, and that one could be for the path itself, and then another stress, normal stress for the path 1, and rather than apply, we do the whole entire selection, and you can see here we got total deformation of what's happening here. So you can see the deformation here is actually 1.3. Sorry, my bad here. I selected the wrong direction. It's supposed to be the total deformation. Solve. There we go here. So 1.3 millimeters is the total deformation. Normal stress. Total deformation here in graph format. So you could take this and copy cells and put it into an Excel sheet. So open up Excel, so Control B, so you've got a deformation there, and then you can go to normal stress, and again here, Control C, go to your Excel, Control V, so you've got stress values there. You just minimize that now for a second. And obviously that's one experiment or one numerical simulation that's been conducted. You can also now duplicate this one, press yes. So it comes here, you can then duplicate, or you can leave that one there, it's absolutely fine. You can go into the setup of this one, change the orientation of the plies, or you can bring in new material, do whatever you wish. So here we've got the element, the stack up here. So here we can change the stacking up sequence to however we wish to do. So the stack up sequence that what we'll take is 0, 45, minus 45, 90, 90, minus 45, 45, and the last one is 0. Press apply, press OK, press update, and our new panel with the new stacking up sequence should be in there. As we can see, I usually you can see the stacking up sequences in here. stacking sequences. It doesn't really matter. I mean, it's absolutely fine, but the angles have been done now in those stacking sequences. So we can just go File, Exit. We can update this one. We can drag and drop another static structural, drop it here, take the model from this one, put it in here, transfer it as a solid composite data. Or what we can do is actually just delete this, because this has already been set up. So what we can do is we can duplicate this one, upstream connection first, that's okay. To give it some time. Why we're duplicating this one is because it has everything set up that we need in order to run the analysis. But what you can see is what it's done is it's taken this data and this one here. So what we want to do is we want to select this one and delete that one, press OK. So we've got that one there, and we can take the setup of this one and put it into here, transfer it as solid composite data. So now it's taken the new orientated composite, but also taken the support analysis. So yes, on there. There's many ways of setting this up. Some may want to do it individually, have their own individual lines, whatever you feel is best in order to conduct your analysis. So obviously it's brought in the new panel, and that's why it's asking for the remote displacement on the new selection. So what we're going to do is select all of these. Am I missing one? Okay, how do we get rid of this? One, 2, 3, 4, 5, 6. Yep, 6 faces. And if I press solve now, it should just automatically resolve it. So mine's already done. So here again, you can see, so the total deformation now is 0.66. Normal stress, total deformation again here. I can take this now for comparison. Control C. Put that in here, Control V. And again here, I can go to normal stress. But here you can see the stresses are completely different because remember, it's not unidirectional anymore. So here it's a lot more different in terms of what's happening, and that's because the middle ply that I've taken here can cause a bit of an issue. So this is actually comparing that one single ply, but the normal stress here you can see because of the orientation of the stacking sequence has created a difference. So when you are creating this normal stress one here, you may wish to take it rather than in the middle of the composite. You might just want to take it on just one single ply, perhaps, you know, for comparison, because otherwise it's going to give you some kind of like, you know, weird results. So you need to be able to keep that value consistent. So when it comes here now, and I paste it in there, Control V, I could easily now insert in a scatter line, select data, here add X value, Y value is going to be this one here. And then I can add in one more, X value of the next one. Y value of the next one here. There we go, and you can see the deflection of model 1 and deflection of model 2. So that's just showing you a quick, unique way of how to do this assignment. I hope it's been encouraging and inspiring. So again, very interested to see what everybody comes up with in terms of the understanding of the different stacking sequences and in order to look at the flexural properties of composites. Okay, so thank you very much.